All right, so let's look at how to balance combustion reactions. So all three of these equations are currently unbalanced. Now, if you're dealing with a hydrocarbon reaction, you're going to have basically three elements here. You're going to have carbon, hydrogen, and oxygen. You're going to want to balance them, carbon first, hydrogen second, and then oxygen third. So the order for balancing CHO. So let's write out what we have on the left and right side of this first reaction. 1 carbon, let's write them in order, 4 hydrogen, and then 2 oxygens. On the right, we have 1 carbon, 2 hydrogens, and 3 oxygens. So, carbons, balanced, great. But I can see that my hydrogens are unbalanced. So I'm going to multiply the H2O by a factor of 2, so now it has a coefficient of 2. That'll change my number of hydrogens to 4, and it'll change my number of oxygens to 4 as well. Now, how am I off? Now my carbons are balanced, my hydrogens are balanced, I just need to balance my oxygens. Luckily, oxygen is the only thing I need to balance, and I have O2, so I have something I can balance that will only change that one element. So, if I need to get it to 4, I'm currently at 2, multiplying by 2. We'll now give both sides a oxygen number of 4. So, now number 2. You should be able to do these by yourself if you wanted to. C3H8 plus O2 becomes CO2 and H2O. Let's just, right now, take this Nope. Great. CHO for this side, I have 3 carbons. I have 8 hydrogens, and I have 2 oxygens. On the right, I have 1 carbon, I have 2 hydrogens, and I have 3 oxygens. So carbons are unbalanced, hydrogens are unbalanced, oxygens unbalanced. Everything's unbalanced. But let's look at the order for balancing and work our way through this process. 3 carbons on the left, 1 carbon on the right. Let's multiply that coefficient for CO2 by 3. That'll now give us 3 carbons and also 7 oxygens. Ooh. All right, I'm going to keep moving on. Hydrogens, I have 8 on the left, 2 on the right. So multiplying the H2O by 4 will give me 8. And that will also change the number of oxygens to 10. But it's okay, I'm still balanced. I still have 3 carbons, 8 hydrogens, 8 hydrogens. Now I just need to worry about oxygen. Oxygen in the O2, I can multiply by 5. And there I go, there's my balanced equation. It's not too bad. CH3CH2OH plus O2 becomes CO2 plus H2O. All right, carbons, 2, hydrogens, 3, 2, 1, 6, oxygens, 2. On the right side, 1 carbon, 2 hydrogen, 3 oxygen. You know I'm bad at handwriting if my 1s and 2s look similar. All right, sure. So now, same process. 1 carbon, let's double it. That'll change my number of carbons and oxygens. So 2 carbons, 5 oxygens. Hydrogen, 6 on the left, 2 on the right, multiply by 3 for the H2O. That'll change the hydrogens and the oxygens. I now have 6 hydrogens, and oxygen I now have 7. More interesting now. So 7 oxygen. Yep, that's right. And now we got to balance oxygen. So oxygen on the left, there's 2, 7 on the right. Well, hard to get a whole number, or hard to multiply 2 by a whole number to get 7. So let's just say if I did try to do this, I would have to do basically 3.5. That would give me 8. 8 on the left, that on the right. Much more difficult. All right, now for the last one, CH3CH2OH plus O2. I have 2 carbons, 3, 2, 1, 6 hydrogens, and then oxygens, 1, 2, 3. On the right side, I have 1 carbon, 2 hydrogen, 3 oxygen. So, carbons, got to balance the right. That'll change my number of carbons and oxygens. Great, that's not right. I had 3, now I will have 5. Now hydrogen, I have 2 on the right, got to multiply it by 3. That'll again change hydrogen and oxygen, so now I have 6. And, come on, where's the math? 7. 3 oxygens on the left side, 7 on the right. Well, how can I get that 3 to a 7? Well, I need 4 more. So if I take O2 and I multiply it by 3, I will now have 6 oxygens there, plus the oxygen in the ethanol will give me 7, and I will be able to balance this out. Definitely a little bit more tricky than the middle one and the top one, but still completely doable with the order of balancing. Now, there we have balanced 3 hydrocarbon combustion reactions, but now all I want to do is show you that you don't have to have hydrocarbons to do a combustion reaction. So when we're adding oxygen to another species, we can consider it a combustion reaction if not otherwise told. So here I have 2H2 combining with O2, becoming 2H2O. This would be an example of a combustion reaction. It's also an example of a synthesis reaction. These are just supposed to be tools so you can see the the combustion of other kind of starting reagents. We can even do it with magnesium. If we oxidize magnesium, we form 2MgO. Still an example of a combustion reaction. We don't actually need to set something on fire to actually do a combustion reaction. Just like here, we're definitely not going to be starting a fire with H2O. All right, so example 7a. C8H18 undergoes a combustion reaction in the presence of excess oxygen. Write out the balance equation for this process. All right, so I have C8H18. reacts with oxygen, O2, and this will form my ideal hydrocarbon combustion products, which are ideally H2O and CO2. So, to balance this, we're just going to go ahead and do the CHO method. Now, I have C8H18, so C8, H18, and then O2. On the right, I have 1 carbon, 2 hydrogens, and 3 oxygens. So balancing, we have 8 CO2, that'll change the number of oxygens. Whoops. So now I have 17. Great, so now carbon's balanced. Now we move on to hydrogen. 18 on the left, 2 on the right. So multiply by 9. We'll change both the hydrogen and oxygen number. Now we have 18 hydrogens and 9 plus 16, 25 oxygens. Well, that's way too many oxygens. So now we have to balance the left side to match the right. O2, 2 oxygens to 25. There is no whole number we can multiply this to get from 2 to 25. It would have to be 12.5, and we don't like to have non-integer coefficients. So we need to have a whole number. So how am I actually going to get that whole number? Just multiply by 2. So instead of having 12.5 as my coefficient, it'll be 25. But a result of that is everything else is going to have to also be multiplied by 2. So 25, 2 for the C8H18, 18 H2O, and then 16 CO2. Now just to make sure, 16 carbons, 36 hydrogens, and 50 oxygens will balance out the right side. 16 carbons, that's good. 36 hydrogens, and 18 plus 32, 50 oxygen. So great, balanced out on both sides. All right, on each of the lines, you don't have lines, identify each reaction as a synthesis, combustion, decomposition, single replacement, or double replacement. Well, CH4 plus O2 becoming CO2 plus H2O. We have the golden reactant here. That's telling me this is a combustion reaction. I produced a more oxidized product when that carbon is reacted. Don't know what I was trying to say there. It's all right. Carbon was oxidized. Now we have a combustion because we reacted with O2 and we produced CO2 and H2O. Next, CO2 becomes CO plus C. This would be a decomposition. We had one element on the left, or one compound, splitting into 2. So, decomposition. FeCl3 plus Na2CO3 becoming Fe2CO3 plus NaCl. Well, let's see what's going on here. We have our Fe, let's do a better color. FeCl3 became Fe2CO3. All right, so my Fe is now bound to CO3 instead of Cl3, and my Cl is now bound to the Na. So we had a complete switch of our cation components and our anion components of both ionic compounds. This will just be a double displacement, or a metathesis reaction. Fe plus S becomes FeS. Cool stuff. That is a synthesis. P4H10 becomes H2O plus H3PO4. This would be a decomposition. NH3 plus O2 becomes NO2 plus H2O. All right, so we are oxidizing NH3. Normally, I would say to myself, well, this could be a combustion or a synthesis. I am oxidizing NH3. That's a good hint. But I'm not going to think that this is necessarily a synthesis just because I am producing two different products. So I don't have multiple becoming one here. So I'm going to say that this is solely a combustion reaction. Lastly, MgBr2 plus I2 becomes MgI2 plus Br2. Well, I have MgBr2 becoming MgI2. I just have an anionic single replacement reaction. My anion just traded places for another anion. So Br2 switch with I2. So single displacement. Great.